this lesson, we'll discuss the fundamentals of quantile regression. We start the discussion with the shortcomings of the typical linear regression model like OLS. Then we provide the background of the quantile regression model. First, we discuss the basic properties of quantiles. Then we discuss the unconditional univariate quantiles. Then we compare conditional mean with conditional quantiles. Then we start the analysis with a simple bivariate problem. We also discuss a simple example and introduce a p-variable problem. Then we start with a dummy variable example in the context of quantile regression. Next, we add nominal variables as regressors. Lastly, we also discuss quantitative regressors in the quantile regression model. In this video, we'll start the discussion with some of the shortcomings of classical linear regression model. We have already discussed the linear regression model. We have also discussed its ordinary least square minimization scheme where we minimize the summation of squares of residuals or regression errors. Let us start with the shortcomings of this LRM or classical linear regression model. It focuses on the conditional mean or that average or that yi bar of the response variable. So ultimately you try to estimate the conditional mean without accounting for the full conditional distributional properties of the response variable. So your response variable yi may have a full spectrum of distribution. However, this linear regression model focuses on the mean, the average value of this response variable. In contrast, if you look at quantile regression model, it facilitates the analysis of conditional distributional properties of response variables. So with quantile regression model, not only you are interested in the median value, which is corresponding to mean, although different. So you're looking at median, but also you're looking at other quantiles, for example, 5 percentile, 10 percentile. So it lets you or gives you the flexibility to estimate the response variable across different quantiles. It is unlike the linear regression model, which is focused totally on the mean. In the scheme that is followed by linear regression model, the means scheme has certain problems in real life data. For example, if whether you're looking at financial market data or any kind of data, you have the following problems. First, data tends to be heteroscedastic. The model assumes homoscedasticity, that means variation of the error term, the sigma square, the variance remains constant. And it also assumes the data is not skewed, it is symmetric, and the kurtosis, which is similar to a normal distribution, a kurtosis of 3, which is similar to normal distribution. So these are some of the assumptions of classical linear regression model. However, in real life business scenarios, the data is not only heteroscedastic, it's sometimes skewed, and also it has kurtosis. Kurtosis means excess peakness and fat tails. So if your data has fatter tails as compared to normal distribution and excess peaks, like this is a higher peak and fatter tails as compared to the normal distribution, the tails are fatter and peak. Also, different shapes of the contributional distribution of response variables. So often there is a shape shifting due to covariates. So because of the nature of covariates or the independent variables, the shape may not be as required for the linear regression model. As theoretically required shapes may not be there. It may change. It may be conditional. Also, another problem is the presence of outlier. So when there is presence of outlier, the mean is affected, not the median and other quantiles are not affected, but mean is affected. So all in all, what we infer that application of linear regression model for practical scenarios is often fraught with challenges in estimation. And to circumvent and avoid those challenges, quantile regression model with its estimation of quantiles rather than mean presents a very good and clean model. In this video, we'll briefly introduce the mechanics of quantile regression model and its background and the motivation. Recall we said that classical regression model focuses on the conditional mean. So if you are looking at a regression of this kind, y1 equal to beta 1 plus beta 2x plus error term, if it is estimated based on classical regression model with the OLS scheme, ordinary least square scheme, you would estimate a value of y, let's call it y hat, which is nothing but expected value of y given x, and that expected value is the expected mean. We call it conditional mean because it is conditional to the values of x. In contrast, quantile regression allows us to study the full conditional distribution of y at different locations. For example, the different locations of y may be 5 percentile, maybe 10 percentile, or 25 percentile, which you call as Q1, or median, which is 50 percentile, may have different behaviors. For example, the differential effect of covariate, that is x, at different quantiles may be different. For example, think if you are studying the income versus expenditure of a family, maybe expenditure on food, surely the families at a lower income may have different food expenditure habits. As a percentage of their income, the food expenditure would be higher as compared to families with very high income. Their food expenditures would be of different nature, and as a fraction of their income may be lower. So there's a different behavior when you study the full spectrum of the dependent variable across its conditional quantiles. And also, if there is a problem of heteroscedasty, that means variance of error term is not constant, or there is a complex shape shift. By shape shift, we mean the impact of covariate on different y is different. For example, if you study the impact of y at lower quantiles of y, the impact of x at lower quantiles versus impact of x on higher quantiles, that may be different. So the shape or the relationship may change over the conditional distribution of y. That is also QRM is fully capable of capturing that. Now, mathematically, if you start with thinking in terms of univariate distributions like y, mean and medians are like centers of the data. And they are often used to define whether the distribution is skewed or not. So when you think of OLS, essentially what you are doing, the mean of the center is the place where you are minimizing from the center the sum of error squares. So here the center is like expected value C, which is the expected value of y. So any deviation, let's consider that as error. So any deviation y minus c is your error ei. So the expected value of this ei square, or typically this this minimization scheme where you are trying to minimize this expectation of square, you will get the mean. So minimizing the deviation square results in a scheme that gives you the mean, or when we transpose it or sort of translate it to the conditional distribution, we get OLS. But in univariate distributions, it is simply the scheme where you minimize the error. Error from what? Error from the center. If you minimize the squares or compute the expectations of these squares, we get the mean. Median is nothing but very similar scheme, but we are not minimizing the squares, we are minimizing the absolute deviation. So if you minimize the absolute sum of deviations or expected value of deviations from the center, which is also the summation of these deviations, you get median. So if I show you in terms of diagram, if this is your univariate distribution of a value and you are trying to, you have a some center C from which deviations are minimized, absolute deviations are minimized, then you get the median. But if you minimize the square deviations, you get mean. So this would be the mean when you are minimizing the square deviations. This would be the median if you are minimizing the absolute deviation distances. So this is the typical scheme to understand what is the mechanics and mathematics behind the quantile regression model as compared to the typical linear regression, which we call as ordinary least square model. So to summarize, in this video, we saw the mechanics behind the QRM model, how it is obtained. It tries to obtain one quantile, which is median. Median is one example of the conditional quantile. There are many such quantiles as we'll see, but median, which is the 50 percentile, is nothing but the center when deviations from the center are minimized in absolute terms. In this video, we'll briefly introduce the concept of quantiles. Simply put, if a student performs better than tau proportion and worse than 1 minus tau proportion of students giving a particular exam, then he or she is considered to have obtained tauth quantile marks. So if it is above 99% and below 1%, then you will call it 99th percentile. This is also expressed in terms of quantiles. Now, any random variable can be characterized by its distribution. So all the variables, they have their distributions, and you also express in the form of cumulative distribution function fy, where fy equal to probability of y less than y. So here a cumulative function is nothing but the probability of y being greater than the remaining y's. So all the y's from which it is greater than the total probability of those y's is fy. For example, let's suppose in a given distribution, a particular value of y is greater than 99% of y's. So the distribution of y is such that 99% values are less than this y or less than equal to, it won't matter much. So then in that case, the probability that y's are less than equal to y is fy, which is equal to 0.99. This is the cumulative probability of that particular value y. Now in this backdrop, quantile function can be defined for a particular quantile tau as q tau, where q tau is inverse of probability, cumulative probability function. So when it is applied on tau, you get a value of y. That means a simple example, let's suppose we said that y is greater than 99% of the values of distribution of y, which means the cumulative probability of y being all the y's being less than y is 99%. That means 99% of y's are less than this. So if we apply, this is also called cumulative function, which is expressed as fy. Now suppose the inverse of fy. So if we apply inverse of fy on this quantile value 0.99, or what we are calling as 99 percentile, then we should get a value of y. So this quantile function is nothing but inverse of, if I apply inverse of probability density function, sort of inverse, which gives you the value of y. So to summarize, in this video, we described how to understand the quantiles and what is a quantile function, which we said is sort of inverse of cumulative probability function. In this video, we'll understand some very basic properties of quantiles that are useful in their applications. One very important property of quantile is monotone equivariance. To start theoretically, any monotone transformation h, such as log or exponential or any similar function of a random variable, one can still obtain the quantiles by applying the same transformation to the quantile function. What do we mean by this? In simple terms, let's say if q is the pth quantile of y, that means if I find pth quantile of y, that is q, then h of q is the pth quantile of h of y. Let's take an example of log. Suppose in a sample data, 20th percentile is 4300 in a given distribution of y. Y is so distributed that 4300 is 20th percentile. And if the data is log transformed, if I transform the data in a logarithmic form, then for the transformed data, the 20th percentile would be log of 4300. So for that log transformed data, 20th percentile would be log of 4300, which is 8.37. So this is monotone equivariance property of quantiles. There is another very useful property of quantile that is often employed, is that these quantiles are insensitive to the influence of outliers. Suppose in a given sample of data x1 to xn with a sample median m, if I transform any value which is lower than median or any value to the higher than median, suppose this value, I by mistake replace this with a very low value, or by mistake a value high with a very high value, anything what is happening on the lower side or higher side, as long as the values are not switching the sides, the median will remain unchanged. So such modifications will not have any effect on the sample median. And similarly, if you look at any quantile also, suppose 25th percentile I'm looking, or 75th percentile, but median is also 50th percentile. So as long as anything is changing here or on the positive side of this 25th percentile, its value will not change. It will remain unaffected. However, the same does not hold for mean. So in this video, we discussed some very basic properties of quantiles. We discussed that they are insensitive to the influence of outliers, and they also follow what we call as monotone equivariance. In this video, we'll fix the ideas behind quantile regression with the help of unconditional univariate quantiles. Let's start. In a very simple terms, univariate quantiles are defined as location of distribution such that the cumulative probability corresponding to a quantile is theta. For example, suppose a particular y defines theta quantile in a distribution of values in y. So y contains a set of value where theta quantile is y. Now, if I accumulate the probability of all the y values that are less than or equal to y, I'll get a cumulative probability theta, and therefore that is the reason why y is theta quantile. If I define a cumulative probability function or CDF such that fy, where fy is nothing but probability of all the y's, cumulative probability of all the y is less than, taking less than value of y, less than equal to y, it's theta. So our typical cumulative CDF is defined as this, which is equal to theta. Here we can define quantile function q theta as inverse of CDF. That means if I apply this q on theta, or in other words, inverse of theta, we'll get that y value where theta is from 0 to 1. Here CDF is typically increasing and continuous. Let's try to visualize that. So I have plotted CDF here, where on x-axis we have set of y values. For example, suppose 25 percentile is 12.2. So 12.2 maps to 25 percentile, while 17.7 maps to 50th percentile, and 23.3 maps to 75th quantile or percentile. So this is our typical CDF, which is rising. Now suppose I want to map quantile with quantile function. So on x-axis I have quantiles like 0, 0 0.2, 0 0.4 and so on. Now recall, if I want to map 25 percentile, I apply function q theta, and recall here 12.2 was the 25th percentile. So the quantile function applied on the 0.5 will give me 12.2. Similarly, quantile function applied on 0.5 will give me 17.7, and quantile function applied on 0.75 will give me 23.3. And this is how we'll map quantiles to their quantile function. So now let us fix the mathematical definitions behind quantile. Recall earlier we defined median as a problem of minimizing. We are minimizing the expectation of a particular absolute residuals from the center. So for example, if y are set of values and c was that centroid median, the errors or deviations from this median centroid could be obtained as this simple problem of minimizing the expectations of these errors or residuals. Let's call them yi's, or it can also be called mu I or yi, which is the deviation from center of y values. Slightly elaborating this concept now, quantiles are also can be thought of as a solution to this minimization problem of this sort. This is nothing but weighted absolute sum of deviations. As we'll see, this is the deviations. Some check function, that loss function or check function rho theta, is applied on them, and that expectation is minimized. And we'll see later, this loss function or check function is nothing but weighted absolute sum of deviations. The idea here is that quantiles act as a specific centers of distribution. For example, median was a kind of center of distribution where 50% values were low and 50% were above. Similarly, 25th percentile or quantile can be thought of as position where 1/4 of the values are less than this and remaining 3/4 are above. So we define our typical loss function rho theta y as this: theta into 1 minus indicator function into y, where indicator function takes a value of 1 when y is less than equal to 0 and 0 when it is positive. Effectively, what is happening, you can think of y, which are the deviations from the center. Some value would be positive and some value would be negative. Now I can expand this like this, where if the in this particular form, if y values are greater than 0, then this will be 0 and you'll have only theta. This value will be 1. So you'll have theta into y, where theta is positive, y is positive. So if y is less than 0, then this value will be 0, this value will be 1, and this will be theta minus 1. So theta minus 1, which will be negative because theta is from 0 to 1, will be multiplied by y, which is also negative. You'll get a positive value. So essentially what is happening, we are multiplying the magnitude of y, or weighing the magnitude of y, with 1 minus theta for negative deviations of y, and weighing it with theta for positive values of y. So effectively you can say we are multiplying magnitude of y with 1 minus theta wherever y's are less than 0, and if they are greater than 0, we are weighing it with theta. And typically this problem can be expressed with this formula, where this is your loss function or check function applied on y. And solution to the minimization problem, the solution would be quantile. So quantile can be defined as solution to this kind of minimization problem, where we are minimizing the expectation of this loss function defined like this. So let's concretize our understanding. We defined a check function or loss function like this, where deviations mu I or yi's are multiplied by tau minus indicator function, which takes a value of 1 when mu is less than 0 and 0 otherwise. Effectively, you are multiplying the absolute values of y with 1 minus tau or theta for negative values of y, and tau with positive values of y, which is nothing but this minimization problem. If you think of it, this minimization problem where loss function or check function on yi minus c is applied, where yi takes a set of values, and here you will have error terms or deviations. These mu i's are deviations, that is, for each yi minus c you'll get some deviation mu I, which will be further fed into this check function, and the minimization problem will give us that centroid or quantile. So effectively what this check function would do, that for all the negative side residuals will be multiplied with mu I would be tau minus 1, and positive residuals mu I would be tau. So effectively it is like saying multiplying mod with 1 minus tau for mu less than 0 and multiplying error residual with tau for mu greater than 0. Recall, if it is half, then you'll get tau as a median. So to summarize, in this video, we tried to formulate our quantile as solutions to minimizing a particular loss function, which is a weighted value of deviations. We were multiplying or weighing the deviations with certain quantiles, and the solution to that problem is the quantile itself. For now, we understood in the form of unconditional univariate distributions. In this video, we'll see a simple proof of quantile regression problem where we'll see how univariate quantiles can be presented as a solution to the minimization problem where we minimize the expectations or summation of absolute residuals. Recall the check loss function that we have discussed is minimization of expectation of this check loss function rho theta, where y we can take as univariate. We can extend this logic to conditional response functions such as a regression model, but think of y as a univariate distributed variable and see some kind of center. Now, for simplicity, rather than check loss, we look at a specific position which is median. And for median, this check loss function minimization becomes this expression. Here y is a continuous random variable and we are trying to minimize the expected value or absolute sum of deviations from a given center C. Now C is some kind of center and we will try to show that this center is indeed median when we minimize this kind of absolute residuals. You can think of y as distributed, some kind of univariate distribution, and fy is the probability density function. So this expectation can be expressed in the form of integral, assuming that y is a continuous random variable. So we can express it like this, where y is a sort of, you can think of a real number. Now this is mod. So this is, we need to make this differentiable over the full range. So without any loss of generalization, we can simplify, we can break it down into two pieces. So for example, this is the first piece where y is less than c. You can think it of as minus infinite to c. And here in the second part, y is greater than c, which is c to infinite. Now we can open the mod and make this function easily differentiable. So from minus infinite to c, we can open this mod by writing c minus y and this as y minus c. So now we have two differentiable functions. We'll look at them piece by piece. We'll first solve this one and then try to apply the same logic to work out the solution for the second term. Now, this kind of function is sort of convex in the sense that it appears like this. So when if you want to minimize this kind of function and you take differential, you'll obtain minima. So when you set del by del differential slope here, you'll get minima because the nature of shape is convex. See, if you recall, the mod appears to be something like, so you'll obtain minima, not maxima. Let's start with this. So we want to differentiate this function with respect to c. We'll set the differential to 0 and find the solution. Now this requires application of Leibniz integral rule for differentiation under the integral side. So there is an integral side. We are looking at first term first. So let's look at this Leibniz rule and try to match term by term basis. Here the limit is from minus infinite to c and we are differentiating with respect to c. First and foremost, look at this expression. Here t is parallel to y, so you can think of this dt as dy, and this function fy, which is your probability density function, this entire combination. Now please notice, because lower limit here is a, which is infinite. Now this infinite is constant, unlike a, which is some function of x, and x here you can think of c. So c itself is c, and the function which is bx upper limit, that is also c. So c bx is also c and c is anyway there. So we take the differential. When you take the differential of this constant term with respect to c, it becomes 0. So this term will be anyway 0. So we'll be left with this term and this term. Interestingly, fy is not a function of c. For fy, there is no c inside. So this will be treated like a constant in this kind of differential when you are differentiating with respect to c. The idea is we are minimizing the function for a given center C. So C is our variable. That's why we are differentiating. See if this is not so clear. And again, we are saying that Bx here is C itself. So when we differentiate C with C, we get a constant. This value will become 1. And you are left with this fx bx, which is nothing but c minus y, because bx is also c and x is also c. So you are left with this function c minus y only. So effectively, the first term will converge to something like c minus y. This will be 1, the constant fy. And you have to find the values at limits minus infinite to c. So this will be 1. What about the second term? Let's examine this. Now here, the limits are minus infinite. So a is minus infinite to c. We are differentiating with respect to c, and the function is c minus y. This fy will be constant fy dy. So when I differentiate with respect to c, I get 1. We'll leave that for some time now, but we have understood that this will be integral minus infinite to c and differentiating del by del c minus y dy. So this is what we are left with after applying this Leibniz rule. So we get this expression. Let's examine this. That's why I did not move forward. I wanted to examine this in more detail. So let's look at the first term. When y equal to c, the upper limit, this becomes 0, right? And recall this fy is nothing but probability density function. So if y equal to minus infinite, at minus infinity, this again, this function will take a value of 0. At minus infinity, a probability density function would behave something like this. So extreme infinite, it will be 0. So this term is fully eliminated. Now let's come back to this. So this term is 0. Let's come back to this. Here, differential of this, like I was saying earlier, this will become 1. So it is nothing but integral of minus infinite to c probability density dy. And this is nothing but cumulative probability minus infinite to c, which is fc itself. The other limit will become 0 because at minus infinite, the value will be 0. Like I said earlier, at minus infinite, there'll be nothing, sort of no probability is there, 0. And the cumulative function at, if you look at the behavior of cumulative probability function, it behaves like this S-shaped kind of function where lower limit is 0. If you look at infinitely on this side 0 and upper limit will be 1. So here it is minus in c to minus infinity. This integral will be fc. In a very identical fashion, the part 2 of this differential, which is this, can also be solved. For example, again, the first term will become 0. If you look at this term, this expression is minus 1. So the only difference here is that differential of earlier was 1, of this term was 1. This term will be minus 1. So you'll have outside minus 1 integrated from c to infinity. Now, you know that when you integrate the right side, this is nothing. If this is fc, cumulative probability fc up till point c, then this is 1 minus fc. So when I integrate this function from c to infinity, essentially what I'm doing, earlier I integrated the left side of it, which was cumulative probability fc. Now I'm integrating c to infinite, which will be nothing but 1 minus fc. So this becomes 1 minus fc multiplied by minus 1. And therefore my overall resulting expression becomes fc minus into 1 minus fc equal to 0. Solving for this, we get 1 by 2. And this is the minimization problem from this approach, minimization problem for a solution to median. The solution will remain same if you use this check function, where the main changes, earlier we have used the weight as same as 1 by 2, but now you are using asymmetrically weighted error terms. Asymmetrically weighted error terms with their magnitude. So we are multiplying asymmetric weights to magnitude of errors. And when you integrate this kind of function will result, which looks daunting, but the solution will be same. Solution, you'll obtain the quantile itself. So we'll not go through the full detailed proof, but when we optimize this problem, the solution, which is this, it is nothing but extension of what we already saw with the median. With other quantiles, the expression will converge to this, and finally this expression will come to here, 1 minus theta into fc minus theta into 1 minus fc, and the solving for this, you get fc as theta. So the center becomes q theta, or quantile itself. So basically the solution to this minimization problem of this expectation with check loss function becomes a generic quantile. For median it was half, and for any generic quantile position theta, it becomes q theta, quantile itself, the quantile value itself. To summarize, in this video, we discussed a simple proof of quantile regression model taken as a univariate quantile, a variable, simple random continuous variable y taken as a univariate quantile. And when we optimize the check loss function for a particular center, the solution we got was quantile itself, and for median we got the value half, which means for the center we got median quantile itself, 50 percentile.